All right, let's talk about Harnack's inequality and Harnack's principle. A couple of results attributed to Harnack, related ones. We've seen one already, um, and this will be this will be the last um, new material lecture uh, for this semester. So we'll sort of, it's kind of a nice. That's what we'll cover, up to here in harmonic functions. An important result. All right, it's basically, what we're doing is we're sort of going through the analogs of some of the stuff that we've seen for holomorphic functions for harmonic functions. All right, so what is Harnack's inequality? The most basic version of it is in a disk. So here it's given in an arbitrary disk of radius capital R in P. Suppose that we have a harmonic function on this disk, and let's suppose it is non-negative. And you noticed it's basically what we usually the results that require some boundedness before for harmonic functions is basically we're looking at non-negative. It's really just bounded from below. You can always move that around, but that's sort of the analog of bounded for holomorphic is non-negative for harmonic. Right? You've seen, for example, Liouville's theorem. The analog for it can be done for there is no entire non-negative harmonic function on the plane. All right, so let's go on. So suppose that we have this harmonic function in the capital R disk, and let's suppose that we take a smaller disk, right? This smallest is of a radius strictly smaller than capital R, and we pick any z in this smaller disk, right? Still centered at the same point. Then what Harnack's inequality says is that we really have some control over how f behaves. We have a bound from above and below in terms of its value at p. You could normalize that to, let's say, be 1 if you wanted to, or something. We have control from both above and below for the value at f of z on this smaller disk. So given that it's harmonic on a bigger disk, we get control on a smaller disk, and it really depends on how small the smaller is compared to the big disk, right? So if you're looking at some disk, the more the larger the disk on which the function has to be harmonic, the better control you have over its growth or how it goes down, right? You have from both above and below, right? So that's what this says. It's sort of we had so various results like this for holomorphic functions. We have something like Schwarz lemma, right? Which also tells you for bounded function, you could if you have a bounded holomorphic function on a disk, and you normalize everything in the right way, then you get some control over how how fast f can grow. You have some inequality. So this is a similar result for harmonic functions. So first, sometimes this when this is given, it's given for a z that is distance r from p, and that's really because this guy increases in little r and this guy decreases in little r. So you might as well, prove this for z in on the boundary of this disk, because if it was inside, you could do it for a smaller little r, right? And that would imply this thing, right? So so let's just suppose that z is on the boundary of this guy, namely it's pli plus r times either I theta for some theta. All right, let S be something less than R, and that's really just because we don't have F on defined on the boundary of this disk. But this is going to be an arbitrary S, and in the end we're going to take a limit. If we prove this with S is over here, we can just take a limit, right? And that's what we're going to do. So first, let's write down f at z using the Dirichlet solution, using the Poisson kernel, and this is why we needed S to be strictly less than R, so that f would be actually defined over here, right? So this is just plugging into the Poisson integral, right? And well, let's rewrite the Poisson kernel. Well, let's actually put a formula up. So we have this formula for the Poisson kernel. All right. Well, let's figure out a bound for this. Well, let's bound this from both sides. What's the best and worst that this can be? So we start with the lower bound, and if you basically you multiply both top and bottom by S plus R, right, to get this expression. So we haven't done anything, and now over here I could stick in this cosine, right, because cosine is between minus 1 and 1, right? So yeah, this is true, right? And if this is true, well, I could move the cosine around and get the thing was a minus over here. And well, now canceling out, well, I cancel out the S minus R, right, because this is now S minus R squared, and we get this inequality that from the bottom we have this bound for the Poisson kernel, and from the top we have this bound, right? So it's just basic basic inequalities, and so now, and this is where we're using a non-negativity, because otherwise we wouldn't be able to compare these integrals, right? Because if you just because I have this inequality, let's say I'm actually looking at the top guy over here. Well, if I want to bound this guy in the formula by the S plus R, S minus R, then I need to actually have that F is positive, because otherwise the inequality would flip, right? So we wouldn't, and might flip differently at different points, so we wouldn't get anything, right? So this is where we're using that F is non-negative, right? And we can bound this from above, but this guy, and we get this formula coming out. Well, that's just the average of F on the boundary of the S disk, and that's just F of P. That's just the mean value property, right? So that means that we got this the the right sort of estimate. Well, at least for S, right? Now the other inequality, the lower one, follows in exactly the same way. We just apply this inequality, right? So you bound from below by, bound the Poisson kernel from below, right? Okay, and once you have this, well, now you have the right inequality just with s's instead of r's, and now, but you have it for an arbitrary s, and so you have it for all. Well, for all s's, so you have it for capital R as well by taking a limit. All right. So the inequalities are optimal in the following sense. You cannot do better without knowing something more about f or the domain or something. So let's look at D, the unit disk, and in the unit disk have a harmonic function f, non-negative. Then the theorem says, it's this, it's these two inequalities. Well, consider essentially just the Poisson kernel, and we're just removing the 1 over 2 pi. So just the important bit of the Poisson kernel. And let's look at what that does. Now, because it's the Poisson kernel, we've shown that that this is positive on the unit disk, right? And furthermore, and this is just directly plugging in. If you plug in 0, we get 1, right? So over here we're gonna get 1s in the inequalities. Well, if we plug in z equals to r, then we get precisely this guy, right? So we get equality over here, right? We get f of z is going to be equal to 1 plus r over 1 minus r, right? And similarly, if we plug in minus r, we get that f is actually 1 minus r over 1 plus r. So we get, again, an equality over here. So that means that these two constants, given this setup, this is the best that we can do. All right. Oops, sorry. All right. So that's for a disk. Now there's this works in other domains, basically just using the idea from the disk, and from the disk we have sort of very explicit bounds. One way to rewrite, change this into a more easier form. I mean, we could do by there will be other ways of writing the inequality. This is a fairly common way of writing this inequality. For an arbitrary u, so that would be the big disk, and an arbitrary compact k would be like the small disk, right? So the Harnack's inequality now says that if I have well, there exists a c, and this c only depends on this k and the u, right? And for every harmonic non-negative function f defined on u, we get this this inequality, that the supremum on k of f is bounded by the some multiple of the infimum of f, right? So we get again if we take the biggest that f can be, it's somehow we bound it in terms of the smallest the f can be. So we have the sort of there's sort of a range of where f is in terms of some values of f, right? All right. So without loss of generality, let's suppose that k is connected, right? How do we do that? Well, so maybe I should say this is, we are assuming that U is a domain. Otherwise, this is not true, and that's a nice exercise to a fairly simple exercise to show why why you cannot drop this domain if you would be disconnected. So let's assume that k is connected. Why can we do this? We can do this, well, first, let's make, if we make k bigger and prove the inequality, yeah, we're done. If it works for a bigger k, it works for a smaller k, right? So you can always make k bigger by covering it by something, right? So let's cover it by finitely many closed disks. You can always do that, but it is still inside U. That means it's just a union. We can assume that it's a union of finitely many disks. Now, that will make sure that k has finitely many components. And if I have finitely many components and U is path connected, I could connect them with some path. I could. You could even make it. A piecewise, polygonal path if you'd want to. It doesn't really matter. So just, I only need to throw in finitely many path. So again, it's still compact, and now it's connected, right? So basically, we just connect k up without leaving U. Right? That's also a point. Now let R be less than half the distance from k to the boundary of U. Right, so k is compact, so it has some positive distance. So let R be something that's less than 1/2. Now, why? Why do we do that? Well, now cover k with finitely many R disks, right? Now, because R is less than half the distance from k to boundary of U, then a 2R disk is still in U, right? Right. So now fix 2 points in k, right? Point zeta and point xi, and we're basically trying to figure out some inequality in terms of zeta and xi in such a way that it does not depend on zeta and xi. We're basically trying to figure out some inequality like this, without the supremum and without the infimum for zeta and xi, and we're trying to get a c that does not depend on zeta and xi. Now, suppose that zeta is in the first disk. I mean, we could just reorder the disk for this to be true, right? And let's suppose that xi is in the nth disk. Let's say it's some little n. It could be less than capital N, just some nth disk. And we could also assume, because k is connected, that that again, by possibly reordering, relabeling these disks, relabeling these points, the intersection between any two subsequent disks is non-empty, right? That we're sort of that we can sort of step through these guys. Now, what what is this going to mean? Well, this is an example setup. So we have a zeta and we have a xi over here, and then well, we're gonna have that zeta is in the first disk, right? And this disk over here, right? And xi is going to be in the last disk. In this case, there's a fourth, right? So that's where xi is. And then we have sort of a path of finitely many disks that overlap, right? So we have Z2, Z3, Z4. Maybe there's other disks, but we don't really care about those. There's at most capital N of these, right? That's going to be key. Now, if what we're going to look at is actually these intervals between the z's. Maybe one more thing is that these larger disks that are marked over here, those are the 2R disks, and those are the point is that they're still in U, right? Okay, because a 2R disk is in U, we can apply Harnack's inequality with capital R being 2R, right? And we get so this is basically in the first disk, right? And we get that f of zeta is less than 3 times f of z1, right? Just by applying Harnack's inequality. Now let q be the midpoint. So remember, before we had those midpoints marked between two subsequent zj and zj plus 1, and it's basically we have this picture over here. We have the zj, we have a zj plus 1, and we have a q over here, and we have these disks. They overlap. Q clearly is on the overlap. Now q need not be on k, so we don't quite know that q is in k. It's just because it's a midpoint of 2 points in k, and so now, if we look at the 2R disk, right, around zj and zj plus 1, we notice that the distance over here from zj to q, and similarly from zj plus 1 to q, is less than r. So just a little bit of trigonometry says that the disk of radius square root of 3r is definitely inside the two big disks, right? So it's not quite a 2r disk around q, but it's still something bigger than some multiple of r, right? So yeah, we have this is a subset of U, and therefore we apply Harnack's inequality. So first time we apply it for this disk, right? And we get a bound for ZJ in terms of FQ, right? Which just we now can cancel the R. We get some fixed constant over here, right? Now we apply it again. Now we apply it with at ZJ plus 1. So Q is in this disk, right? So we get this inequality over here, right? So we just get we get this extra factor, right? And canceling out blah blah blah, right? We get 3, right? So we get this this guy over here. All right. Well, finally, if we're at the nth one, we apply just like in the first one, and we get we get this inequality, right? Because C was in K, so the 2R disk is around C, right? It's still in U. And putting all that together, basically, taking the first inequality, then going to Z1, then going to the Q between Z1 and Z2, and so on, all the way up to Zn, and then going to ZC, where we'll get, there's n steps. We get a 3 in the beginning, 3 in the end, and then for each step in between, we get one of these factors over here. Now this n is, well, that's less than or equal to capital N, right? So we get this constant over here. Now, capital N, that's the only thing that this depends on. That didn't depend on the C or the zeta. That was just something that depended on K. However many disks we needed to cover K by, right? And that's it. All right. That's we now take the supremum over zeta and the infimum over Xi, and we get the term, right? All right. So let's look at an application of this, so-called Harnack's principle. There's a couple of versions of this. So let's do this one. For an increasing sequence. There's similarly one for any sequence. If we get pointwise conversions, we get uniform conversions. But so that's an exercise in the notes. But let's look at this. Suppose that we have an increasing sequence of harmonic functions, right? Any domain, any increasing sequence of harmonic functions. Nothing else. We know nothing else about this, right? But we get actually, there's two possibilities. Either f goes to infinity uniformly on compact sets, or it converges to a harmonic function uniformly on compact sets, right? So we get, we start with essentially no convergence at all, and we get basically, if you're going to get infinity at one point, you're going to get infinity at every point, then you're actually going to get it uniformly on compact sets. And if you're not going to go to infinity at any one point, you're actually going to get a limit at every point, and the sequence converges uniformly on compact sets. So this is an amazing result in some sense, right? And you can prove a variant of Montel's theorem, for harmonic functions with this. So it's that kind of a theorem, right? So first, without loss of generality, assume that these are all non-negative. Why can you do that? Well, you can always subtract the first one, right, from all of them, and then the first one would be 0, and you'd get that they're all non-negative. Now, monotonicity says that a sequence pointwise you get some sort of convergence, possibly to infinity, right? So it's you get convergence to some real number or plus infinity, right? Now, if the limit is plus infinity for some p at some single p of u, then let K be any compact set that includes p. We apply Harnack's inequality and get that, because P is in K, right? And really, you can take any K and throw in P, and you get a compact set, including P, right? So we're gonna get something for all for all K, really. So if we get Fn at P, which we know goes to infinity, as n goes, well, this is, I can just take the supremum over all Z in K. P is in K, right? And now Harnack says that this is less than or equal to C, and this C only depends on K. The infimum of the Fn's over K. All right. Well, what does that mean? That means that if I have this basically tells me that the infimum of F sub n's on K goes to infinity. Well, that means that that F sub n goes to plus infinity uniformly on K, right? Because I get if I want it to be bigger than sum m, I can just give you, whatever n I need to make this bigger than sum m, and that gives me that this is bigger than sum m, divided by c if you'd want to, for all K, right? So this is uniform. All right. Well, so we have that if the limit is infinite for some P, then it's actually infinite for every P, and we actually get that that the sequence goes to infinity uniformly in compact subsets. So suppose the limit is finite for some Z. Well, the same thing would be, suppose that it's the sequence is at a single point it's bounded, right, above. Right? That's really all that we need to show. Well, then we have some sort of a limit, a real limit everywhere. So let's define a function, little f. So real valued function on R. Let that be the limit, and let K be compact, and C is the that's the C from Harnack's inequality, right? For this compact, any compact. Now, given any epsilon, suppose that m and n are such that we get this inequality. Well, why can we do that? Well, because at some p, at some p, we have a Cauchy Cauchy sequence, right? Because it's the limit exists at every point, and it's increasing. That's why I don't need the absolute value signs over here, and so we can pick an m and an n such that this is true, right? And then we get that for that m and n, the supremum of fm minus fn. Well, that's bounded by Harnack, by this thing, right? By the infimum times c, and then we get that means that I can plug in that specific point p, and I will get it that's less than epsilon. So whenever we have this thing, we have that the supremum is less than the epsilon, right? So so from that I can conclude that that the sequence is uniformly Cauchy on K, right? And if it's uniformly Cauchy on K, it converges uniformly, right, on K. Therefore, F is harmonic by Harnack's theorem, right? I have a sequence of harmonic functions converging uniformly on compact sets, therefore the limit is harmonic. This is, an amazing result. Sort of unexpected that you would get something like this, right? But it's, that's something that we maybe, came to expect, right? As I said in the beginning of this class, complex analysis is sort of the Alice in Wonderland kind of area. You get anything that you that you think is true is actually true, even if it almost makes no sense. Very much unlike unlike real analysis, where even reasonable things are not true, right? So here, just because we have an increase in sequence, it almost works like if it were numbers, right? That that you get a limit, right? It's either infinity or harmonic, right? It's almost like what you would get for a sequence of real numbers, right? Monotone sequence. It's kind of weird that you would get it for functions, and all you need is harmonic, right? The other thing is that you get this uniformity on compacts, right? Why would you get uniformity, right? I mean, that's a weird thing. Why would the rate at which you get these go uniformly? And it's exactly this being able to get handle on sort of how, if I know how far K is inside U, I can get some handle on how far apart can harmonic function be at 2 points, right? I have some control over it that only depends on K, and of course non-negativity, right? Which gives us some bound somewhere, right? So that's the point, right? If you didn't, if the Harnack's inequality, if you didn't put in, if it wasn't for non-negative functions, then it wouldn't be true. So all right.